Final May 3rd, it's 10 a.m. And so it'll be over everything that we talked about. There's one final homework assignment that's due Wednesday, right? And so I will say, I don't think we'll be able to get to the canonical form today. So I'm going to say, so for lab 7, omit problem 4C. After today, you should be able to do the rest of it. Should be, at this point, should be able to do the first 2. And then the next 2, most of the next 2 after today. So there are any questions?
I have questions.
Yeah.
So for that exercise you gave us in class to find the GI and the Elias effects. So I noticed, I don't know if I did something wrong, but I want to go through that. I noticed that some interactions were Elias with more than one main effect.
Yeah, that's possible. Sure it is. You know, I think that one you had 31 effects, right? And you had 3 defining contrasts, right? Okay, so 31 minus 3 is 28. Okay, and you only had like 4 observations, so you can estimate 3 things. So of course, some of those main effects are going to be A-list with interactions. Maybe they're going to be with some more than one interaction. But I thought it was just one. C and D were the only A-list ones I thought, but maybe not.
Well, my question is like, because some interactions were being Elias with more than one main effect. Is that?
Yeah, oh yeah, of course, yeah. Right, in fact, C and D were going to be A-list with a bunch of interactions. Both C and D were A-list with a bunch of interactions.
And also on that same topic, so I guess in class what we were doing is we were listing the main effects and then checking everything that was Elias with them.
Mm-hmm.
And then in some books I noticed that they do like main effect Elias with this, and then 2 ways with this, and 3 ways with that. So they kind of break that down. What's the difference? Like, how do you?
Well, of course, that makes sense if you got enough degrees of freedom to just start and see what the A-lists are with the main effects, what the A-lists are with the 2-way interactions, and so on. But in this case, we only have 3 degrees of freedom. So, you want to focus on the main effects first. And it's clear you can't estimate all 4 main effects with only 3 degrees of freedom. So there's going to be aliasing. But yeah, that's the idea, sure. You didn't have enough degrees of freedom to really even look at the rest of those things, right?
Okay, but yeah, I guess I'm just not quite clear to me how you would do, like, because they have like this main effect Elias relates with whatever 2 ways, and then whatever 2 ways Elias with 3 ways, so it's like just a pair of one Elias with another, and not like a.
Yeah, that's more complex than that. Life is a lot more complex than that, usually, right?
So that's not.
Well, I mean, what I would do is, okay, just take the main effects first, and then try to get all the aliases and see if you can count for the 31 effects. If you can't, then put the 2 ways in there and get their aliases and see if you can count for all 31 effects, and so on. And by the time you've got to where you can count for all 31 effects, you don't need to look at any more, because all the aliases are there, and you can see all the structure, right? Okay. Other questions? All right, so we're talking about response surface methodology. And the idea of response surface is kind of 3 goals. Or 3 objectives. The goal of response surface methods is to find the input combinations or the levels of the independent variables that optimize some response. So that's the overall goal. So optimize, I mean either maximize or minimize. Okay, so for example, you might want to know how much vitamin C and how much protein I should give to growing pigs. Okay, I want to maximize their average daily gain. What are those levels of vitamin C and protein I should have in their diet to maximize their growth? Okay, that kind of thing. So the independent variables are all continuous. Now, we haven't talked about restricting what the independent variables are up until we've talked to this. Anything we've talked about up to this point can be applied to quantitative variables or to categorical variables. Here we're talking about just categorical independent variables. Of course, the dependent variable is assumed to be quantitative. Okay, so there's three things there. First thing we want to do is find the area near the optimum. Okay, second thing is that we'd like to be able to find experiments or run experiments in the area of the optimum. Okay, once in this region, once in this area, run experiments in the area of the optimum, in this area. And then, of course, the third one is to estimate the surface, the optimum point or the stationary point, and explore the surface. Okay, so I'll try to do these sequentially. All right, so let's look at the first one, finding the area near the optimum. There are a number of different ways to do this. Historically, probably, well, in my job, my experience is people use this one. And I think it's the worst thing you can do, finding the area near the optimum. One way is run one big experiment. Okay, so say you have 4 factors. And you have 4 factors, and you want to minimize the number of runs. So you do one great big experiment, and you do central composite design. And the problem is that the central composite design, which we'll talk about, is based on the assumption that the surface is nice and smooth. Well, usually if you run one great big experiment, then it's difficult to find what the surface really looks like. Surface is very irregular, usually. Surface is very irregular and difficult to find the optimum. So how many master's programs have I been on? They got 4 or 5 factors. They come in, even PhDs, say, yeah, we decided to run a central composite design with 4 factors, and we did it with only 28 runs, and we got this really nice data, and now I want to look like what the surface looks like. Unfortunately, I say you can't do anything with the data. You can't find the optimum because the surface is too complex. Okay, you need to get in the area of the optimum first. Okay, so just avoid this if you can. Avoid this approach. Now, of course, what do the master students say? They say, oh, I've got 2 years. My advisor told me to run this experiment. I ran it, and I got the data. Now I got to go over statistics and get them to help me analyze the data. You can't find the optimum. The surface is so irregular. Okay, you see what I mean? So we need to be getting the area of the optimum so we can, it's simple, and we can estimate a simple surface to find out where the optimum is. Another approach that people use is one factor at a time approach. And you can see this in Giesbrecht and Gumpertz. And I know Cox, let's see, this is, I can't remember what section this is, 1510 maybe? I can't remember. The Cochran and Cox, it's in 8A.5. Cochran and Cox. And I'm not going to say any more about this other than what you do is you start with one factor. You hold all the other factors constant, and you try to find the optimum in that direction. And okay, now I found the optimum in the first direction. Now let's go to the second variable. Hold all the other factors constant. First variable factor will hold at that optimum level. Now we'll go in the second direction, hold everything else constant, and then find its optimum. And then you sequentially proceed through that. So it's what it is a sequence of single factor experiments. Now this will work pretty well, and it's easy to understand. You can explain to people easily. It's competitive with the steepest descent methodology, which I'll talk about in a minute. But the problem is it works poorly when there's interaction. Well, we better have a method that can deal with interaction. If you know you don't have the interaction between your factors, well, then that should work. Exactly. Okay, the method I'd like to talk about is the method of steep descent. There are other methods. There's one called a simplex method, another one Project gradient method. Maybe I'll just say that here. See Giesbrecht and Gumberts for other methods. See Giesbrecht and Gumberts 1510 for other methods. But what I'm going to talk about is response, or steepest descent. You've got to understand this first before you again understand the simplex of the conjugate gradient method. So I'll talk about the steepest descent. Now the idea is we're going to start with some small experiments. Well, think if you're blind, okay, and you want to get to the top of a mountain. Okay, your friends take you and drop you off, right? And you're blind. You want to climb the top of the mountain. What are you going to do first? You're going to feel down and try to feel which way the direction is going, and you walk that way for a while, right? Well, if you start going down, what are you going to do? You're going to stop. Yeah, it might drop off. Stop, and they'll feel which way to go. Great, I think blind people do that, right? It's exactly what steepest descent is. Okay, now, maybe if you think of, okay, what I have to do is I have to bend down and feel the soil. Okay, it's dropping off that way. I want to go that way. And I'm going to turn this way and bend down and feel the soil. That kind of goes that way. The fact that you're going to bend down and do this is a little 2x2 factorial experiment. Right? And now based on that little factorial experiment, you're going to get a direction. And you're going that direction for a while until you start to drop off. You see the idea? Now see if I can write this in a sentence that you'll understand. So using small 2 to the n experiment, we get an initial direction. And then proceed in that direction until the response starts to decrease. Until the response starts to decrease. Then stop. Do another. Run another 2 to the n experiment. Get a new path of steepest descent. And continue. And of course, we're going to continue until what? We're going to continue until no more increase is evident. Continue until no more increase is evident. This would work great for a blind person, but you better be fair to them. You better get them to the top of the mountain, pretty close to the top of the mountain. If they're not at the top of the mountain, they're going to find what? They're going to find a local option, right? Not a global. You want to find the top of the mountain. You better get close to the top of the mountain before you let them out, right? Everybody see the idea? Okay, let's do an example here. And one we talked about is baking brownies to find questions. Can you read my writing? So let's do something that everybody can relate to. Hopefully nobody has to climb mountains if they're blind, although there hasn't. Recently there was a guy that got to the top of his blind at Mount Everest. Amazing thing, you know. Especially that one face, it drops off and goes down almost 10,000 feet. You know, I was in the North Face. So, anyway, okay, so an example. We're going to do easier things. Baking brownies. We want to bake brownies. And we want to find the best tasting combinations of chocolate and sugar. Best tasting combination. Chocolate and sugar. What are the factors? Chocolate and sugar. What's the response? Taste. Okay. So, you know, you bake brownies, and you have to have an oven. You talk about baking experiments. Well, that's what this is. So I have baked pan of brownies and give everybody a slice, and they taste and give a score, right? And I take that mean score of that pan of brownies. Okay, so I get one response for every pan. Okay. So the first thing I want to do, I'm going to use pass the steepest descent. First thing is run an initial two-to-the-n experiment. Run an initial two-to-the-n experiment at the best estimate of the optimum. So you take your mother's recipe for brownies and you want to improve on it, right? Well, it may not be possible, well, because these recipes are interesting. Historically, they may go back thousands of years. You know, the Egyptians were baking wheat 5,000 years ago. So some of the stuff we put in our food, it has our history, human history, the food we eat is very interesting. But anyway, it's probably going to be hard to beat your mother's recipe is what I'm saying. But you start the best recipe, okay? Now, my two factors I'm going to look at are I'm going to call it E1 and E2, just for different notation. So this is chocolate. And then this is going to be sugar. Now I'm going to start at the center. I'm going to say 1 cup. That's going to be the best. This will be the best recipe. I'm going to start at 1 cup of chocolate and 0.5 cups of sugar. This is our best estimate of the optimum. So that's it. We're going to start there. Okay. Now before I bake that pan of brownies, I'm going to deviate. I'm going to take a range. The range here is going to be plus or minus 0.5 cup. So I'm going to go up half a cup and down half a cup from 1. And I'm going to do, the range is then going to be, the range is going to be 1. And so in this case, I'm going to grade 1.25 cup. That's going to be the range. Now, how should we vary these? How far should I vary when I talk about the levels? Because as an experimenter, this is your only choice. What levels do I have? What levels should I put? Well, if I go, what I want is I just want these little two-to-the-n experiments, I just want a direction. I don't want to get any curvature in there, but I want them to be far enough apart to be able to see a trend. Okay? So I don't know, I will just say these are far enough apart to see a trend, but not have much quadratic. Okay, you see what I mean? Okay, so the range would be what? 1.5 down to 0.5. That range, 1.5 to 0.5, is going to get some sort of response in the taste, but hopefully it doesn't go up and down. It's not too far. And the same with the sugar. Okay, so we don't vary that too much, but enough to get a response. Okay, now what we do is we code these things, and these are the variables that we're going to use in design. So x1 is going to be E1 minus the center point divided by half the range. And so x2 is going to be a coded variable, E2 minus the center point there, which is 0.5, over its half its range, which is 0.25. Okay, now, what I'm going to do is I'm going to have a little 2 by 2 factorial. So what will the levels be? So my design then is going to look like this. So the design is going to be a 2 squared factorial plus some center points. Okay, so what's x1 and x2 for the 2 by 2 factorial? Let's look at x's value now. Now if I go down 1, or down half a cup, it's going to be minus 1, right? If I go up half a cup, it's going to be plus 1. So my coded values are going to be minus 1 plus 1, right? So if I go down half a cup, it's 0.5. Okay, so 1 minus 0.5 divided by 0.5 is minus 1, right? So my coefficients are my x values are going to look like this. 1, 1, minus 1, 1, minus 1, minus 1, minus 1, 1. Okay? Okay, that's just 2 by 2 factorial. How many pans of brownies am I baking now? 4, right? Here's recipe. Okay? So I have high, this one's going to be what? High sugar, or high chocolate, low sugar. This one's going to be high chocolate, high sugar, low chocolate, low sugar, and low chocolate, high sugar. Which one are we going to like? Probably this one, right? High chocolate, well, if you like chocolate. I did this ice cream with this class one time, and one of the students said, "Oh, I'd rather eat the bowl ice cream, ice cream." Well, no, Tisha. She says, "Well, I hate chocolate." So maybe it depends. There's variation there. That's variation among people, you see. Okay, variation among judges. What else? I put some center points. Where are my center points in this design? That's the center points, right? And those are going to be 0. All right, so let's put 4 center points in here. Okay, 0, 0, 0, 0 for both of them. Okay, so this is the factorial portion and then center points. This is what's called a first order design. It's when we have a factorial and some center points, and we're not going to really be interested in estimating interactions here. Okay, so these are the factorial, and these are the center points. Okay, so that's our first little experiment. Okay. Now why, look, if I'm a blind person on the side of a hill, why do I have to bend down 4 times and feel the soil at the same time every time? Everybody see what I mean? That makes no sense. Probably makes no sense to have 4 center points because you're staying at the same place. Why would you, as an experimenter, have to have 4 center points?
Define your direction.
Well, this is going to get our direction. Here's my picture here. Right, I got a little 2 by 2. Here's my center points. Right, and then here are my factorial points. Right. Why do I need to run that multiple times? I mean, I look at the surface. I can get the surface without having no center points at all. Waste my time, really. Am I?
Control. Like a control.
Yeah, it's a control, but why do you do the same thing over and over? We didn't up here. Are we wasting our experimental material? Well, that's okay.
I don't. You have to do it 4 times?
Well, I could just do it once.
Yeah.
Okay. What's wrong with that?
You need to repeat it so you get a pretty good measure of yourself.
Well, yeah, but there's something even more important. Anybody? Dr. Muhammad. Huh? Come on.
Does that have something to do with the optimum, the global optimum, resident global?
Oh, there's only 2 things in statistics. What are they?
Alice?
Mean. Now that's kind of what we're talking about here. We're getting the mean responses, right? What else?
Alice?
Variance. You know what happens if there's huge variation here among these things? You might not trust anything coming out of this, right? There's just so much noise in the system. What are you going to have to do? Well, you might have to replicate these points themselves. You see what I mean? And so you have center points to estimate some sort of variance. Now, we're not so interested in testing significance in steepest descent. We're just interested in estimating the surface. But it is useful to have some idea how well the surface fits. Okay, so let's estimate the surface. So that's step one, estimate the surface. So we're going to have our model as this. This is the first order model. Expected value of y is equal to b0 plus b1x1 plus b2x2. This is what's called the first order model. The first order terms are really just the main effects. And in this case, they're very simple. They're just linear main effects, right? That's it. This is called the first order design. Okay. So the simplest model we can fit would be this one. Okay. Let's look at the ANOVA. I mean, you all should be able to get the X matrix out of this without any problem. Let's look at the ANOVA. Maybe it'll be more clear about why we have those center points. Okay, what's my number look like? If I got 8 hands, I got 7 degrees of freedom. And the source of variation is going to be x1, which will be our chocolate effect, which will be 1 degree of freedom. x2, which will be our sugar effect, which is 1. And then air is going to be 5, right? So I have 5 degrees of freedom for air out here. So air, 5, right? Well, some things missing that we actually could estimate. What's missing here from the way we usually have been analyzing these things? Interaction. Right. Where does it go? It goes down here. Okay, so well, we're going to have to take 1 degree of freedom for interaction. Right? It still needs some other stuff down here. Right? Okay, so I can break this out into 1 degree of freedom for interaction. Okay, which is the, let's see, 1 degree of freedom for x1 by x2. That's 1 degree of freedom. Okay, now let's look at this. How many degrees of freedom do I have over here among these 3 center points? 3. Okay. So I got 3 for, that's called pure air. Pure air is the variance among the center points. That's 3 degrees of freedom. What's going on here? Right? Well, that should add up to 5. What am I missing? Let me try to draw a picture here. Here's my factorial points. And here's my center point, right? Now, okay, I didn't have a center point. I got 3 degrees of freedom. I'm done. There they are. 1, 2, 3. Right? If I didn't have a center point, there's 3 degrees of freedom, that's it. But I got this center point here. Okay? And I know I got 3 degrees of freedom among those 4 center points. But there's something else going on. Can anybody see it? We got the interaction here. There's another one. Here's one that's a mystery point. What is it? That variation?
That would be like center point and interaction.
Yeah, well, the center point, right. What this one is the center versus everything else. If I take everything else, okay, everything else versus the center. So others versus the center. What's that measure? So I can take the others, y bar others minus y bar the center, right? What does that measure? You see what I'm doing?
Direction.
Oh, no, we got the interaction here.
I mean, the direction of the epsilon.
Well, no, but the direction could be based on it's going to affect the direction kind of, but that's really getting closer. Well, what happens at this point is way up here. And now the other ones are down here on the board. So this point's way out there. Because this is my y-axis coming out this way, right? So this point's way out there. What does that tell you about that surface? Is it flat? No. What is it? There's curvature. If that's significant, okay, we have curvature. So this is curvature, or maybe I'll say curvature, or factorial center versus others. Okay, curvature. Now you're not sure which way the curvature is due to. Is it going this way or is it going that way? You can't separate the two. But it certainly sees there's some curvature there, right? What happens if the center point is a lot harder? You do this little experiment, center point's a lot larger than the others. That might tell you what? You're at the top, right? So there's information in this curvature. Now we could do a little test on it. How would we test that? What statistical test could we use here? Simplest test that 218 students hopefully know. T-test, right? We can do a t-test on this. Other minus the center over, then we have to take the standard deviation. This would be pure error. We get the mean square from the pure error and take the square root of that, and then divide by 1 over the number of factorial points, or other points, minus 1 over the center points, right, or plus 1 over the number of center points, right? It's just a t-test. So we can do a t-test simply. Of course, the way we do this is analysis of variance. Okay, so we can evaluate the surface. So that's a useful reason, is we want to have center points. What this whole thing here is called, you put these two together, that's 2 degrees of freedom for what? Does anybody know? 2 degrees of freedom for the test for lack of fit. The model we're fitting is this. If this is significant, that says that model doesn't fit very well. Okay. 2 degrees of freedom tap for lack of fit. That's really important if you're doing these kinds of models, is that you have a lack of fit test to decide whether you need to do something else. Especially at the end of the experiment. You do one great big experiment and you got a huge lack of fit, what are you going to do? I don't know. You may not be able to estimate things you want to estimate. In fact, we had exactly this problem with a PhD defense last week. He just flat couldn't run the things he needed to run. So we knew it had a significant lack of fit, but what the heck it means, we're not sure. Well, we didn't keep him getting his PhD, but he just couldn't run it. He didn't have the right stuff. He was in Uganda, and you only got limitations in Uganda. So. Okay, so we got an estimate of the surface. Assume it fits. Assume there's no lack of fit. We want that to be small. Okay. We can say this. Okay. If the B's are large, B's of I's are large, we need to move in another direction. Right? If they're small, all small, or all small, what does that mean? And lack of fit is large. Lack of fit, LOF. Lack of fit is large. What does that mean? Those slopes, well, it looks like that, right? You might be near the optimum. Could be near the optimum, maybe. What do? Better run some more, right? Okay, before you totally decide, commit that's the optimum, then you need to, let's get a path. Let's run some and see if it really does improve in one direction or another. Okay, okay, so, no, I'll say, no, test of significance. Not very important at this point. Not very important here. Because we're really not testing significance, we're just trying to get direction. Mostly interested in just a direction. What is this direction? what is this direction? Tests of significance are not very important here at this point we're talking about. We're mostly interested in the direction, but what is this direction? So this is number 3. This direction is called the path of steepest descent. And so what is it? Well, I can get my predicted model to look like this. B0 plus B1 x1 plus B2 x2, where the B's are the estimates of the betas up here. Okay, so I can get that. And what does that mean? If I move 1 unit of x, how many units should I move in x1? How many units should I move in the x2? Well, what we can do is we can differentiate the function. We can differentiate with respect to B1 and differentiate what I have with respect to B2. Well, I expect you to do this. And when you differentiate, we get this B1 and B2. Okay? Now what is that? Well, we want that to be as large as possible. What are these? We want to increase the response as much as possible. Now, you might want to make this a decrease as much as possible, depending on what you're doing. You know, it might be you want to get to minimize impurities or something in your process. So you might want to minimize it, not steepest descent, and what steepest descent. Okay. But anyway, we get these slopes. Now, if I want to increase the response, what do? Here's my x1 matrix, x1 vector, and say I want to go B1 units this way. If I go B1 units that way, how many units should I go for the B2? I should go B2 units in the x2 direction. This is my path. So this is B2. So this would be 0 here. I want to go B1 units here. If I go B1 units, to stay on that path, I want to go B2 units in the x2 direction. So what that means is if you move 1 unit in the x1 direction, you move 1 unit in the x1 direction, this is B1. Then I want to move how many units in the B2 direction? Okay, so then move B2 over B1 units in the x2 direction. And all that is a slope. If I move 1 unit in the B1 direction, right? How much do I have to move 1 unit in the B1 direction? Then I have to move what? B2 over B1 in the B2 direction. Right? It's just the slope. That's all it is. Okay, so we just get the slope. So this tells us how far we move in the x2 direction, given we know that we move 1 unit in the B1 direction. Okay, and in general, this is going to be Bj over B1 for xj variable in the general case. Okay. So if we move 1 unit in the x1 direction, then we know once we have the path, we can know which direction we go in all the others. Okay, let's do an example. Questions on any of this? Okay, let's do a little example. Let's assume that we have some data. In fact, this is problem 3 in your homework, I think. Right. So let's assume assume y hat is equal to 3 plus 0.1 x1 plus 0.2 x2. That's my estimated response. I took my data from first order design and estimated that. And I think it's a reasonable model, or mean reasonable service. So if I move 1 unit of X1, and so how much is that? If I move 1 unit of X1, what's my units in chocolate? The unit, or 0.5, right? 0.5 is in the unit. So this is the same thing. If I move 1 unit of X1, that's the same thing as equal to 0.5 cups of chocolate. Because you got to translate it. Okay? And what does that mean then? If we do that, then we're going to have to move 2 units. This would be the 1 unit of X1 is a half cup of chocolate. Okay? And then that means because I got, why did I move 2? Why is it 2? It's 0.2 over 0.1, right? 0.2 over 0.1. So it's 2 units of X2. And how many cups is that? It's 0.5 cups of sugar too, right? Because 1 unit is 0.25, so this is the 0.5 cups of sugar. Okay, so let's run some points here. So perform some runs on the path. Now, this is more experimental work. I first originally did my experiment with 8 pans of brownies. I baked 8 pans of brownies, and you all tested them. I got a mean response for each pan of brownies. I did 8 pans. Now I got the path of steepest descent from those 8 pans. Now let's do some more pans of brownies. Bake some more pans of brownies on the path. Okay, so we're going to have to bake some more brownies. Okay, and then we'll get the response. Get the y's for each. And then compare the y observed to the y hat. Okay, and so when they really start to deviate, then you can stop. So let's actually calculate these things. Now I don't have any real data, so I can't. In this simple example, I didn't have any real data, but let's put a table up here. Kind of makes it easier to see. Okay, so let's say here's my x1 value, and it's going to take values of 0, 1, 2, and 3. Okay, so I start in the center, and I go up by half a cup, right, then go up by another half cup, and so on, with chocolate. Okay, now x2, I can do the same thing. I'm going to go up by 0. We start at 0, but if I go up by 1 unit of x1, I got to go 2 units of x2, right? And then I got to go 4 units here, and I got to go 6 units here, because I go up twice the number of units for x2 compared to x1. That's what I'm talking about here, right? B1 is B1 over B2, or B2 over B1. B2 over B1. Right. Okay, so say we get the observed value. Well, actually, we can relate this to, let's relate this to our E's. Okay, if I can erase this a little bit. So that's chocolate and sugar. And so this, let's let E1, what's E1 equal to? E1 is going to be equal to 2, what is it, 2 times x1? No, 0.5 times E1. I'm sorry. Yeah, it's 0.5 times x1 plus 1, right? Well, that'd be my E1 value. So what are they going to be over here? My E1 values are then going to be 1. If I just calculate, that's just 1, right? That's a decent. I'm going to start at 1 cup of sugar. Okay, and then I plug in x11, so this is going to be 1.5 cups of sugar. And this will be 2 cups of sugar. And this will be 2.5 cups of, chocolate. This is chocolate. And then E2 is going to be what? It's going to be, it's 0.25 x2 plus, what is it? 0.5, right? So its values are going to be what? Well, it's going to start off at 0.5 cup, which is what we did. Okay, and then I go to 1, and then it's just going up to 0.5 cup also, so 1.5 and 2. So these are the new recipes you'll run, right? But we do everything in our coded space. Everything's in terms of coded space, but it's easy to code back. We can code them in this way to know what you have to do with your experiment. So now you get my observed. So I get my y observed here. So I get y1, y2, y3, and y4. My 4 runs on the path. And then I get my predicteds. So my predicteds here are going to be b0 plus b1x1 plus b2x2, right? In our case, this is what? 3 plus 0.1x1 plus 0.2x2. So I get the predictions. And so I have predictions for the first one on the path, the second one on the path, the third one on the path, and the fourth one on the path. So perform some runs on the path and get y for each, compare the y observed to y. So what happens if this one's really close to that one? What would you do? If the predicted and the observed are really close, what should you do? I'm going on the path now. What's my own idea here? What am I trying to do? Trying to get to the top, right? So if the observed is really close to the predicted, that's, you have to bake 4 pans of brownies, and I get the taste of that 4th pan. That's really close. What do I conclude? Is the model doing a good job or not? Model's doing a good job, right? We got quite a bit of improvement. What next? Just run some more. You're making progress. Keep going in that direction, right? What happens if it really starts to deviate here? All of a sudden, y4 hat is a lot larger than the observed. What does that mean?
You cannot go behind that.
Yeah, well, you shouldn't go beyond it because what you're doing, you're decreasing the response. Okay, so don't go any further in that direction. So if there's a big difference between the observed and the predicted, especially if the observed is a lot lower than the predicted, you better stop. Then what? What should you do?
Move back.
Yeah, find another direction. So the blind person walks along until it starts falling off a little bit, right? Stop, reassess the situation, walks along again, right? Good. So these are the points on the path that you measure to see how far, are you really dropping or not. Okay? So what's the next step in path steepest descent? Steepest descent methodology. Depends. If the observed is close to the predicted, whatever that means, then continue along the path. Continue making runs along the path. So if observed, y hat observed is near whatever that means, y hat, then continue on the path. Continue making more runs or experimental units on the path. If y observed is less than by a fair amount, as it's less than by the predicted, then stop and run another 2 to the end, right? Now, my question is, what happens if the observed is a lot bigger than the predicted? What do you do? I don't know. You're doing okay in that direction. Maybe you should just keep going in that direction for a while. Until maybe it's ridiculous and you say, well, I better stop because maybe you can make more progress. Okay? So it's not really clear if the y observed is a lot greater than the predicted. But so if the y observed is much greater, then I don't know. Maybe maybe should stop and run another. Why? If we stop and run another, we maybe get a faster steepest descent. Okay, and we're saving our experimental units. Okay, but maybe not. This is judgment call. Lots of stuff's judgment calls, right? Okay, so this so we've kind of finished up in terms of how we finish this thing. We can keep repeating this. So the final step. So we repeat steps 1 through 3. Repeat steps 1 to 3 until the bees are small. Until the bees are small and or large lack of fit. Now the idea of large lack of fit means that, hopefully it's tall in the middle, not if it's below in the middle. So the final step, repeat 1 and 3 until the bees are small and or we have large lack of fit. Okay. And then when either of these happen, then we're near the top. Then, near the top. Near the optimum. Okay? So this is the third problem I want you to do. It's using steep descent. So there are questions out of this idea.
So like when you say stop and run another 2 to the n experiment, but then what do you change?
Well, yeah, good question. What would you do? Well, I would run another one maybe right here. I think in the homework assignment, the logical thing is you get your last one, and you decide, well, maybe I'm going to run one here. I might want to go back or fit a little bit better, and then run a little 2 to the n around that point. You see what I'm saying? So pictorially, you start down here, and you get this direction, you go out like this, and it gets worse, and you run another one, and say, these are your 4 points. Say this is 1, 2, 3, and that's the 4th point. Maybe you run another one around that. See what I'm saying? And then you get another direction. Okay? So it's kind of judgmental in terms of where you stop here. But you don't want to go down. So if you run another 2 to the n back here, if that thing is really quite a bit lower, you probably wouldn't want to do that. You go back to your best point, right, where it fits pretty well and you have a pretty good response.
So do you have to have overlapping levels between different
No
ones,
way.
or-
You just get that path, and if you keep increasing, you're going to get way, way far away. Once you're on a ridge, or you're on the side of the hill, and you keep going. Why do any more experiments? Or just do some more runs, do some more little experiments on the path, right? Yeah, it's very practical. Okay, now, so that's kind of the first thing, is to get in an area near the optimum. Okay, now, let's talk a little bit about designs and analysis near the optimum. Okay. This is kind of like the second step, design and analysis near the optimum. And the first thing I like to do is talk about a second order model. We're going to kind of do it backwards, talk about the analysis first. Second order model. Now, if we're near the optimum, hopefully it looks something like this. Here's my y value going this way, and it's something like this. Hopefully it's just like an inverted bowl, in multiple directions. Because the problem with all these things, we could be talking about 10 dimensions here. How do you look at a surface in 10 dimensions? That's a difficult problem. But the algebra all holds, see. But ideally we're at the top of a mountain that looks something like this. Most mountains I've been on top of, they're kind of like that. As long as you get close to the top, they're a lot like that. But you got to get that close first. Okay, so now if we're close enough to the top, a little simple model like that's going to work, and that's called a second order model. And so the idea is if you're near the top, you do near the top a simple quadratic model with interaction, with linear bilinear interaction, should fit well, should fit reasonably well. So this is just a simple regression model. And what's the second order model look like? Here's my prediction. It's going to be B0 plus B1x1 plus B2x2. Now this would be for just two independent variables. I already got chocolate and sugar. Okay, so then I fit linears first, then I fit quadratics plus B22x2 squared. Plus, then I got a B1 term, which is the cross product, or just the interaction term. So that's a second order model. And it's simple. It's just quadratics. Well, if you have quadratics, you have the linears in there too. So it's a simple quadratic model with a linear bilinear interaction. That's it. And that should do a pretty good fit of a surface that looks like this. Now, one thing, why do we want to fit this model? Why don't we just fit all the terms? Well, you may not be able to fit all the terms. You're trying to minimize your effort. The one thing that's powerful about this is if you're close enough to the top, that's going to fit pretty well. But maybe the most important thing is you can save a lot of experimental material by realizing that this model is going to fit. I don't need to have too many points because I don't have too many parameters to fit. Okay? So note, if they're n factors, here I got 2 factors in the example, then we require a minimum How many number of runs are we going to have? Minimum number of runs as, what's our minimum number of runs if this is our model? Absolute minimum. Now we talk about fractions, that should be easy for you. How many parameters are we going to estimate? Seven or 6? 6. If you forget about experimental error, you can estimate 6 parameters with 6 runs. But that's the minimum now, right? Those designs that have the minimum number of points are called small composite designs. I'm not going to spend much time on it. But look, I can fit that with only 6 points. Now usually what you do is you have a couple center points. Okay? That's pretty good. Okay? So we need a minimum number of runs as 2 to the n plus n times n minus 1 over 2 plus 1 experimental units or runs. To fit that thing. So in this example, 2 to the n, well, if I got the n factors, this would be 2 to the 2, that's 4, plus, this is the 2 to the 2 is 4, it's 4. 1, 2, 3, 4. Then this is a cross product term or the interaction, and one of those, 1, and then this is 6. So if you look at n, I'll make a little table here. N is 2, 3, here's the number of factors, 4, 5, and so on. For the second order model, let's define this as second order model. We're going to have at least 6 points to fit the second order model. Okay, what's the full factorial look like? Full factorial. Well, how many points is the full factorial? Well, 4. That's not helping us any, right? We'll fit more points. Okay, for the full factorial, we can't fit these quadratic terms. Good. 2 by 2 factorial, so we're taking more points. Okay. How about a 3 to the n? If I have 3 levels on each one of these, then this is going to be 9 points here, right? Okay, let's say I have 3 factors. Then the second order model is I'm going to have a minimum of 10 points. Okay, the 3 to the n is going to be 8, and then the 3 cubed is going to be 27. Look, we're starting to get, compared to the 3 to the n, we're starting to get a lot of savings in terms of the number of points we have to estimate. Okay, if I have 4 factors, then I need, for the second order model, I need a minimum of 15 points. I'll need, 32 to the, no, that's 16. 16 is 81. And then if I got 5, let's just do 6 here. 6 is 28, 64, and 729. Now, what do people like to run around here? They love factorials. And how can you fit a quadratic model without at least 3 levels? Well, the competitor is a 3 to the n. If I want to fit quadratic to every one of these factors, I'm going to have a 3 to the n. And wow, look at this. Compare 729 compared to a minimum of 28. Huge savings. Okay. This is why people like using second order models with some of these response service designs, which I'll have to talk about next time. But let's talk a little bit about the analysis of second order models, because this is problem 4. The analysis of second order models. When we get data from a central composite design. And I'll talk about that next time. So the analysis of second order models. Well, so we already have our model over here. Okay, let's just get the ANOVA for this thing. So the ANOVA is source of variation, and then total degrees of freedom is going to be, let's assume that I'm going to do a central composite design. We'll have a full factorial with 4, 2 to the n, 2 squared is 4 factorial points, plus we'll have 4 axial points, and I'll talk about that. Plus, so that's 8, plus we're going to have 4 center points. Okay, now what does the picture look like? Central composite design looks like this. Here are my factorial points. Here's my center point, and then I've got these axial points that are out here. So I'm going to have a total of then 12 points. So I got 2 squared, plus I put these axial points on, okay, and I'll talk about that next time, and then I have 4 center points. And so I'm going to assume I have data from that. And that's what you have for experiment, for your homework assignment. Okay, so let's get the sources of variation. You'll have x1 for 1 degree of freedom for the linear, x2, 1 degree of freedom for the linear, x1 squared, 1 degree of freedom, x2 squared, 1 degree of freedom, x1, x2, which will be 1 degree of freedom. And the lack of fit, which we talked about, we can partition 3 degrees of freedom, and then air is going to be 3 degrees of freedom. Now notice, if I look at my factorial points, how many points do I have here? How many combinations do I have? I got 4 here, that's 8, plus 1 is 9, okay? My factorial structure, I should be able to get 8 degrees of freedom among the factorial structure. 8 degrees of freedom. And then part of them are in here. So I've got 5 degrees of freedom here. Okay, I got 3 more degrees of freedom down here. Right? And that's how I get this other 3. So I got 5 degrees, 8 degrees of freedom for the 9 points. Okay. And why 3 degrees of freedom for air? Because I got 4 center points. Okay. So I think in this homework assignment, you need to be able to get lack of fit and test. Look, there's a test for lack of fit. If that's significant, what does it tell you? What does it tell you about this model over here? There's a problem with it somehow. Okay, now it's hard to say what the problem is often. Okay, is it the fact that we should have a quadratic bilinear term out here? Well, which quadratic linear term? This is only linear bilinear interaction. You could have quadratic bilinear, linear by quadratic, and quadratic by quadratic. Those are three extra terms that we could have out there, but it's hard to estimate these things. One thing you can do is to test to see if you have a significant lack of fit, and we get an F ratio here. This I have an F ratio of 3 and 3 degrees of freedom. But you just get the means here. So I'd say what you need to do when you analyze these, especially response service model, the first thing is to test for lack of fit. If lack of fit is not significant, then what you should do? So if lack of fit is not significant, then what? Probably just pool those together, right? That's saying, oh, well, that's just estimating error anyway. The lack of fit is estimating error. Maybe you can pool then. Then maybe pool. Okay, pool the pure air plus the lack of fit. So this is really pure air here. Pure air. This is what I called air before with the first order model. Right. So you may even pool pure air plus lack of fit. Okay. If it's significant, then what? What do we do? Better be careful about the model, right? Let's just say at this point, be careful. So that's what Robert had last week. So what's the committee do? Basically said, you can't do any more runs. He's going to do his PhD. Be careful using the data. I don't know. Ideally, what would you do? If you had more time and money, you could add some more points to your design. That's called design repair. Okay? First design didn't work very well, so you go back in and try to repair it by doing some more runs. Well, there's some problems with that, but that could give you enough information to figure out where the model is not fitting very well. But if you're going to estimate a surface, that'd be the first thing you do. Second thing you do is once you have a final model, once decide if model is okay, then test significance of the individual terms. So now I can test significance on each one of these. Okay, and if a term is, well, I'll say this: if an interaction term, if a term is significant, the final model must include that term. So, for example, x2 is significant. If a term is significant, then include that term and all its lower order components. Its lower order components in the model. So what I mean by that, so for example would be, say for example, let's say you do the test of significance and you only find this one significant. Say, tests show only x2 star is x2 squared is significant. Then what is the final model? It's got to be included, plus its lower order component, which is what? X2. Plus you got to include the intercept. That's it. Okay, then the final model will be y plus b0 plus b2 x2 plus b22 x2 squared. Right? How about if x1, x2 is significant? This would be 1, final model. 2, if x1, x2 is significant, and x2 squared is significant, then what? What's the final model? So this is significant, so now I'll say this one is significant, and this one is significant, right? All terms except x1 squared, right? Okay, so y hat equals b0 plus b1 x1 plus b2 x2 plus, now no quadratic on b1, so b2 2 x2 squared plus b1 2 x1 x2, right? Okay, so there's a system that you need to use when you're looking at polynomial models to kind of come up with the final one. Now this is important. This is important. Why? What are you trying to do? You're trying to estimate this final surface. And if you put in a whole bunch of squirrely terms, you put them all in, a bunch of them are not significant, you can get this surface really looking crazy, and you're going to get an optimum out there that's probably not going to be very trustworthy. Okay? So you need to make sure you get a pretty good final model by going through this process. Important, since the final surface can be very sensitive, to non-significant terms. So this rule is very important. Okay. If a term is significant, include that term and all its lower order components in the final model. Okay, now hopefully that's enough for you to get through the steepest descent problem and then that one problem on fitting that response surface. Next time I'll talk about the designs, the simple composite designs, maybe Bosch-Bacon designs, how to get to axial point, and then end up with some examples. And I'll see you next time.